Thank you for everything. Really appreciate it.
No problem, Warren. All right, opening the webinar in 5, 4, 3, 2. Good luck.
Good afternoon, everyone. We'll get started shortly. People are still rolling in. I'm just watching the numbers here. We'll just give it another couple seconds. Okay, why don't we start? Good afternoon, everyone. Welcome to today's Future Supply Actions Funding webinar. I'm Warren Teitz. I'm a team manager within Metropolitan's Water Resource Management Group. Been the lead for the Future Supply Actions Funding Program, and I'll be your moderator for today. Next slide, please. So first, a few housekeeping items. We'll do some introductions, presentation, and then the Q&A. But we are recording today's webinar. It will be posted on our website a couple days afterwards, along with the final report and the slides. We hope to have time for questions at the end. So please type your questions in the Q&A. We have muted your microphones, though, for the duration of the webinar. Next slide, please. So first, a little bit about Metropolitan. We are the nation's largest wholesaler. We deliver water from the east, from the Colorado River through our aqueduct, and we also import water from Northern California through the State Water Project. We serve 19 million people. We're a wholesaler, so we sell it through 26 of our member agencies. We support half the state of California, $1 trillion economy, 830 miles of large diameter pipe, 5 of the largest water treatment plants in the country, about 1,800 employees, and about a $2 billion budget. So we're big, and an important part of Southern California's water supply. Next slide, please. But we're more than just a water wholesaler. Over the past 30 years, we've been diversifying our supply portfolio, or the region's supply portfolio, with investments in conservation, recycling, groundwater recovery, loss of storage and exchange programs, Diamond Valley Reservoir. And this is, we expect to do this in the future, expanding our portfolio with a one water approach. And even though this is a great year, it's a good ski year, so it's a great water year, we need to do more. We still have shortages in the Colorado River in the future, and we need to invest in our system in long-term resiliency and innovate. We need to innovate or die, and this is where our Future Supply Action Funding Program comes in. Next slide, please. So we established our the Future Supply Action Funding Program in our 2010 Integrated Resources Plan with the goal of driving innovation in groundwater, stormwater, reuse, and desalination, basically local resources. The goal is to pilot new approaches and new technologies so that we can de-risk them. Water agencies by nature are risk adverse, and this is how we get new technologies into our plants, into our facilities. We want to remove barriers with this program. We want to remove institutional barriers, regulatory barriers, financial barriers, and technical barriers. And finally, even though these studies are done by member agencies like Las Virgenes, we want them to benefit the region. So I think you'll see from this webinar that even though this is Las Virgenes' study and they're doing it on their demonstration facility, this will benefit other pure water projects throughout throughout Southern California. All right, next slide, please. We're wrapping up our current round of studies. We invested 3.1 million in about 14 member agency studies, including this one. We also funded just under $1 million with the Water Research Foundation. That included 6 potable reuse studies and 1 agricultural reuse study. And our funding partner for most of those studies was the State Water Resources Control Board. And so we were happy to have that partnership. Next slide, please. So at this point, I want to turn it over to the Las Virgenes, and in particular, John Zhao, who is the Director of Facilities and Operations at Las Virgenes. So John, please take it away, and I'll see you at the end for Q&A.
Thank you, Warren. My name is John Zhao. I'm the Director of Facility and Operation with the Las Virgenes Municipal Water District. Before I introduce today's speaker, I wanted to thank Warren and his staff and the Metropolitan Water District Southern California's Future Supply Action Program that enable us to drive the innovation in the water industry that would ultimately benefit our customers, which we all serve. I also wanted to acknowledge our sponsors for this study. They are obviously Metropolitan Water District of Southern California. We also have U.S. Bureau of Reclamation. We have the National Alliance for Water Innovation within the Department of Energy. We have Yokogawa Corporation of Japan. And also we have a METI that stands for Ministry of Economy, Technology, Industry of Japan. We have NEDO, which stands for New Energy Industry Technology Development Organization of Japan. And we also have NWRI, which is the National Water Research Institute. And in addition, we have the partner agencies I want to acknowledge. Metropolitan Water District Southern California be the partner agency, and my agency, which is Las Virgenes Municipal Water District. We also have Orange County Water District, West Basin Municipal Water District, LA Sanitation Department, that's City of LA, also Baylor University, and the U.S. Military Academy at West Point, along with Coral Engineers, and also IO site, which we use to congregate data from many different platforms in order to perform the study. So with that, I'd like to introduce today's speaker. We have Daryl Johnson, who is the Water System Manager for the Las Virgenes Municipal Water District. He's going to talk about our demonstration project. And we have Andy Solvenson and Amos Branch from Coral Engineer, who is the principal scientist who performed the AI and machine learning study, who will talk in depth about their findings. Next slide, please. So just a quick brief of Las Virgenes Municipal Water District. We are partner agency through a joint power authority with Triumphal Water and Sanitation District. Together, we serve about 95,000 people over about 150 square miles. To the lower left is a picture of the Tapia Water Reclamation Facility, and which treat about 9.5 million gallons of wastewater daily. To the lower right is the famous Surf Right Beach. In the wintertime, we discharge recycled water through the Malibu Creek and into the ocean and through the Surf Right, famous Surf Right Beach. To the upper right is our Rancho composting facility. Because we do not have enough land at the Tapia Water Reclamation Facility, we have to build a separate facility that's processed biosolids, digest it, and compost it about 4 miles away. And to the upper left, we have the Las Virgenes Reservoir, which is about has a capacity of 9,600 acre feet. And just a side note, because of the rain, we were able to accumulate 4 times as much more water as a normal year to the runoff from the surrounding hillsides. So that's just to show how much rain we had this year. Next slide, please. So the drivers, why we want to build a pure water project. So the driver to build a pure water project is a regulatory. In 2017, we received a NPDES permit, which is based on the TMDL rule from US EPA, that mandate that our discharge in the summertime, the nitrogen is 1 milligram per liter and the phosphorus is 0.1. For those of you in the water industry, you know the MCL level for drinking water for nitrogen is a 10. So we need to treat the water 10 times cleaner than the drinking water level before we discharge into Malibu Creek. In the wintertime, it's 4 milligram per liter for nitrogen and 0.2 milligram per liter for phosphorus. And the regulatory deadline is 2030. And we're hoping to build our full-scale advanced water treatment plant based on the experience we get from the demonstration project. We're hoping to finish the full-scale project by 2080. Next slide, please. So with a regulatory requirement like this, we embarked on a stakeholder process to figure out what's the best way to meet the regulatory compliance need. So we looked at seasonal storage. We say, well, in the wintertime, can we store the recycled water in a reservoir? And then we can use it during the summertime. As you know, to build a reservoir in the Santa Monica Mountain is not an easy task, if it's not impossible. We also looked at, can we upgrade our water reclamation facility at Tapia to treat the water to that level before we discharge into Malibu Creek? And the third option we looked at is, can we utilize potable reuse? We need to treat the water to 1 milligram per liter of nitrogen. Can we use potable reuse via reservoir water augmentation? Meaning, can we treat the water in the wintertime and put this exceptional quality water into our Las Virgenes reservoir and then use it during the summertime? And the stakeholder unanimously agree that the potable water via reservoir water augmentation is the project we should embark on. Next slide, please. So with that, we were looking at a little bit down the road, what it takes to build and operate a AWTF. We looked at our water reclamation facility. We'll also look at the future need for the AWTF. And what we discover is it's very energy intensive. Our staff is the best in the industry. We staff our water reclamation facility 9 hours a day. And the rest of the time we use SCADA to run the facility 24/7, 365 days a year. So we want to continue that pattern of operation. And we want to see if we can utilize artificial intelligence and machine learning so that is it possible to make, in addition to the biological and the physical barrier, we can build using AI and machine learning for a virtual barrier, meaning not only we can reduce energy use, we can safeguard water quality, in the same time, also discover issues ahead of time and make a timely decision while try to prolong the life of equipment that we're relying on in order to deliver exceptional drinking water to our customers. Next slide, please. So here's a picture of a close picture of the Tapia water reclamation facility. To the lower of the picture is the Malibu Creek, and to the upper portion of the picture is a hillside. As you know, we maximize the use with the current treatment technology. There's no rooms available. So we decided to build our pure water demonstration project. We repurpose our old headquarter buildings. So there's three goals we want to accomplish. The first is that we want the pure water demonstration project that's catered to our customers, that people can understand the process, people can relatively assured by through the visiting the demonstration project, receive the education documents that the water is safe. So it's so we designed that, as you can see. Goal number one is for our customers. There's a interactive process. Goal number two is to training our operators. As you know, as I just said, we wanted to build and operate our ADBTF by 2028. So we want to train our operators who can step into operating their facility, shorten the learning curve. And number third is we wanted to test technologies such as the AI and the machine learning that you'll be hearing from Andy and Amos, that we're hoping that going through that, not only will we contribute to our own success, but also to the success of the industry. Next slide, please. So next, I'll hand it over to Daryl Johnson, who's going to provide a little bit of detailed information for our pure water demonstration project. Daryl?
Hello, everyone. Thank you for attending today. Within our demonstration facility, John talked about our three goals, which are very important to us. We are using MF, UF, RO system, and UVAOP. These are all full-scale equipment that we're using. So training our operator staff is very important to us, and giving the customers a true idea and a sense of what the equipment will look like. We are running the facility 24 hours a day. We're treating it as a full-scale facility, and we're currently cross-training 4 people. So it's been a great tool for us, and also a great tool with working with the AI and the future of machine learning. Next slide. We also have a lot of current AI work that's going on. Amos and Andy will both touch on this as we move forward, but our task one is model predictive control to reduce energy consumption. That one, and then we have task two, the pathogen-based advanced water purification control. Both of these are Bureau grants with NWRI, and these are critical to our goals in meeting the direction that we want to go when we move into our full-scale facility. And next, I'll turn it over to Amos Branch with Corollo Engineering.
Hi everyone, how you going? Sorry about the sloppy slide start. I was waiting for someone else to move the slides along. So what we're going to do is we're going to start at Tapia, and because this is a little late in the day, everything got delayed by COVID, we've actually progressed quite a lot. But what I'm hoping you'll realize is that this seed funding from Metropolitan on this initial grant actually kickstarted a whole lot of really interesting research, which Andy is going to go into a bit more later. We're letting the snowball roll on and to try and identify where and what is possible and what's worth it when trying to apply machine learning and artificial intelligence. So the primary goal when we looked at Tapia was to keep nutrient and removal performance at the same excellent level that it was, but to try and drop airflow requirements and thereby reduce power consumption. Now, there's a lot of models and ways you can do this. There's people who've built up solids retention time control strategies based on activated sludge models, and they work quite well. But what we did was a little different. We were partnered with Yokogawa Electric Corporation, who have used this data-driven model optimization control strategy previously on oil and gas type optimization issues at oil and gas plants. And this was sort of a first step is, well, can we apply this to a water reclamation facility, and where does it get it? So the initial 2 steps and the steps as part of this grant were all offline. So Los Virgenes provided their operating data, all the historian tags. That went over to Japan. Yokogawa fit their model to it and started to run what if scenarios of, well, this is how you're operating now. Could we potentially do any better if we change set points in a more timely manner? So the initial results were quite good. We were able to predict the general trends in data, and we were able to indicate that if you made a few slight changes, there could be about 10% potential energy savings. This resulted in a marginal increase in effluent ammonia, but that marginal increase we're talking about is sort of from typically non-detect values to just being able to see it. Also simulated an optimization with a goal of reduced ammonia, and we could do that if you wanted to push it down even lower to non-detect all the time. You could achieve that with only increasing energy consumption by 2.7%. So there are a lot of ways in which you could use this tool. Subsequent to that first step, and it's still as part of this Metropolitan supported grant, Las Virgenes actually upgraded the blowers, and we thought, oh, this might be game over. They've got these fancy new blowers in there now, this new hardware. Wonder if we can still bring anything. So we actually repeated this desktop application, and there was still potential for energy savings, still potential for around that 10%. And there was further monitoring installed during this second stage, which allows us to also demonstrate a potential for a slight reduction in total nitrogen as well, while still saving that 10% energy. So we were pretty encouraged by these results, but the whole work package so far, I mean, it does use a machine learning approach. DDMO falls under that banner, but I wouldn't say it's automated, and I wouldn't say it's convenient. It takes a SCADA historian expert time to download all that data. It took our colleagues at Yokogawa time to fit their models, evaluate model accuracy. And what we really want is an actionable tool. So based on this work and using the results from this work, we're able to put forward a solid bit of evidence and actually progress this to the next stage. And the next stage is get it done in real time, get it done automatically, and give the advice to your operators. So this is where Las Virgenes had already started working with IOSite, who are a data management company who have these really pretty dashboards. And we were able to pull in the tags from IOSite, get them shipped over to Yokogawa in Japan, and automate model predictive control based recommendations as to what should be happening should the operators wish to sort of optimize their control strategy. And so the status quo is set the DO at something you know that works and leave it there. What this allowed was recommendations for that DO set point based on influent flow, influent ammonia, and general plant loading throughout the day. And we were able to trial it in real time. So I'll just show you one of the other dashboards now in terms of monitoring the actual impact, monitoring the changes were implemented to give evidence that the process was actually doing something. And at the end of this, what we realized is that you could potentially shave, depending on what basis you looked at it, either a kilowatt hours per pound of ammonia treated of around 25% just from making these simple changes. We only did that during 8 hours a day, or somewhere around 10% if we just looked at that base energy usage. So depending on how you wanted to look at it, there could be some quite useful savings there. So moving downstream, so the next thing is, let's have a look at the potential energy savings at an advanced water purification facility, and what could we potentially do with micro and ultrafiltration. So at the demonstration plant, we do have those 3 different independently monitored and operated microfiltration membranes. They're all operated on the same feed source to help guide decisions on procurement and membrane operation. Fairly typical operating set points. We're not trying to break the mold here. We're trying to develop design criteria. But a unique opportunity, because this is generating data in quite a large proportion of the time. So almost 3 years of operational data now with 24/7 operation and an uptime sort of over 94% for all of those units. The trick when you are trying to operate membrane systems, though, as compared to, say, a wastewater treatment process, is you're generally getting really good quality, but you really need to balance how well you design these systems and how hard you can push them as to whether they can resist changes in water quality. So the way we express that is if you've got really bad water quality, you've got a lot of what we call foulants in there, so just stuff that comes in and reduces the performance of your membranes. And the way we can address that is either by pushing less flow through the membrane, so operating at a lower flux. Unfortunately, that means you have to buy more membranes if you need to treat a certain flow. Or we can do things like pre-treatment. We can add other unit operations or perhaps chemical dosages in front. We can do different chemical cleaning frequency and regimes. And we can also adjust backwash parameters, so non-chemical physical based cleaning techniques. And all of that together puts you either in a good place, which is cheap to operate. You're never really in the red in terms of transmembrane pressure, so how hard you need to push to get your desired flow. And if you're not in that sustainable zone, then you've got an imbalance, and at a worst case, this can be incredibly difficult to come back from. You're paying more dollars in terms of energy required to filter that water, and potentially more dollars in terms of chemicals required to continually clean back those membranes. So this was something supported by the metropolitan work, and it was, well, what would be useful with a membrane system? I know what would be useful. Can we predict the future behavior? Can we sort of, at a first step, look at where we're going to be down the track? Because what this allows us to do is actually judge whether we are in a sustainable zone or not, theoretically, based on past performance. And it also allows us to start optimizing things like chemical cleaning practices. So I didn't make it easy for Yokogawa. At the end of November 2020, so this is with about 5 months of full scale of operating data from the demo, I told them I'm going to operate like this for the remainder of December. You tell me what my transmembrane pressure is going to be. And what they told me was the black line, and what actually eventuated when I gave them the full set of results at the end of December was the blue dots. So sure enough, it's a real plant. There's some variability, but what I think is really quite important to point out is that they really did do quite a good job of nailing that central tendency. So we started to get excited about our capability and capacity to start predicting the future, basically, and started to think about applications which we could use this. Now, I have circled a couple of outliers. The first one's not our machine learning model's fault. That's my fault. I increased the flux. I didn't tell them. We expect that. And then the second one is actually us conducting a recovery clean. So that's a deep clean of these membrane systems. It had only happened 3 or 4 times before this. So the model hadn't really had a good chance to bite at a training set to encompass that event. But otherwise, this was quite promising. So we moved on then, and Yokogawa sort of revised and improved that model. So they discriminated it into 2 different parts. And what I liked about this approach, it's moving towards explainable AI as opposed to black box AI, which is we're trying to target incremental things that we know are inputs and work with those, because that makes it a lot easier to understand what this AI model is doing and what it is doing its predictions based on. So a couple of the things that were isolated were the fouling rate, so the change in permeability historically, and also the delta permeability that happens when you enact chemical clean. And so you take those 2 models based on past performance and then use them to predict the future. So we did a whole lot of training during the 2nd year of operations, moved around some fairly wacky operational parameters to try and expand the potential range of conditions under which this model could gain some training set and validation set information from. Now, I do want to tell everyone, even though we had that pretty staggeringly good whole month worth of predictions, that the weatherman never seems to get in trouble for making bad forecasts. And we didn't want to judge this too hard either, but we did test it hard. And the reason we've got this in there is we do have the preconception that the further we try and predict into the future, the less accurate it's probably going to be. So we wanted to test this model and say, well, how inaccurate are we going to get? So in terms of the sort of second set of data I'm going to show you, we said, well, Yokogawa, we've got 3 months left in the evaluation period where we can start playing with parameters. This is how we intend to operate. Tell us what's going to happen 3 months down the line at day one of our trial after you've had sort of this training set to work with. And then we started to investigate the accuracy of that. So in week one, so from day 0, the red line is the predictions, the blue line is the actual data. A mean absolute percentage error of about 5% and a root mean squared error of about 0.3 GFD per PSI. Now, the particular membrane we're looking at typically operates around 8 to 7, so 0.3 seemed to be pretty good accuracy. Moving into week 2, so this prediction, pushing it further out, it's starting to drift down. It's starting to suggest performance should be lower than we're actually getting. But we're still within sort of 10% error or an absolute error of half a gallons per square foot per day per PSI. Moving into the 3rd week, sort of pushing that error out again to 10%, but still around half a gallons per square foot per PSI. I do want to point out one thing though, that even though we are getting inaccurate, we do have a bias within the model, which is actually suggesting our future results are going to be worse than they actually are. And what that allows, and that was done by design, was to actually put a conservative estimate on where performance was going to be so as to not run into big problems and not be able to fix them. What I should also point out is that unfortunately we made it difficult for our friends again, because they called us back up and said, look, there's something wrong with your cleaning. It's just not matching up. And we're pretty sure in our model. And sure enough, we checked with the site and they said, oh yeah, the hypo injection quill to the CIP tank broke last week. So we made it even harder for the model, but it was still able to sort of track within 10% accuracy. So given we were becoming quite confident with this model, we started to think, well, what are the best ways in which we can use this? And if you think about an actual project, you've kind of designed the system, you've already installed the equipment for the most part. By the time you would potentially be thinking about doing something like this. So with all membrane systems, if you don't want them to foul, turn the flux down. But in reality, at a full-scale plant, you can't just say, I'm not going to treat as much water because I don't want my membranes to foul. It's not really a useful recommendation. However, what is useful is using the what-if capability of these models. So it's pretty typical to clean membrane systems with 500 milligrams per litre of free chlorine twice a week or once a week. So if we look and use our what if capability with this model, we can say, well, that'll give you one sort of predicted future TMP curve. But what happens if we try and reduce that chemical usage, but maintain the same sort of starting and ending TMP you get with the status quo? What the model was able to suggest was a strategy that resulted in 60% less cleaning, which is quite cool because that's 60% less cleaning chemicals. That's a reduction in potential downtime. And when we presented this recently, one of the operators said, oh, well, we've had real big hypo shortages recently. Is this something I could use to try and get by with the small amount of hypochlorite I've had delivered? And I thought, yeah, I mean, that's exactly what it's for. So what this actually resulted in, it's not a super pretty dashboard, but it was one we were able to make as part of a fairly small research grant where we had sort of this AI model built in, operating with real-time data into an interface where operators could come in and put in a few decision criteria and either simulate the future or ask for an optimized recommendation for various cleaning set points and issues. And so this was a dashboard set to sort of manage that data and try and make it usable, try and put it in a form which could be used and actually assist with operations. So those are the sort of sets of results we've gotten through so far, none of which wouldn't have been possible without this initial seed funding. But where do we think we're headed? I mean, there's these big brands of intelligent water, and we're sort of on this semi-autonomous operation track. So what tools do we have with machine learning in the middle? What algorithms can we develop? And what actions are there to achieve our goals? And that action to achieve goals, and then if you wanted to do fully autonomous operations, so bring on the Skynet, that could come back around and that could be part of the control system. At the moment, we're working on trying to provide better decision support for human operators. So this would be a segregated recommendations platform like we've already put together. And what it does, and the advantages of it are, it's a system that continuously interrogates data and continually provides recommendations. So it doesn't have the lag of sitting there and downloading SCADA data. It doesn't have the lag of having a semi-competent person know what calculations to do on that SCADA data to actually come up with key performance indicators and recommendations based off those. Another advantage we see of this approach is that it can have a hard interlock to stop some concerns about cybersecurity. So if you're only taking data from a historian and you're not able to send commands back, that does remove one of the ways in which this could be misused unintentionally. So just thought I'd round this out with a few pretty pictures of some of the other sort of aspects of this grant that sort of got built into where we did try and automate some of these packages. It's called Optics. It's USBR funded, but obviously not possible without this original seed funding. So we did identify that with these particular applications, there's different stakeholders, they need different levels of access. And so this says VT SCADA on it. It's not a SCADA platform. This is actually a web-based interface. So depending on your level of access, as long as you've got a Google Chrome or a Firefox or a Microsoft Edge, if you're that way inclined, you can actually access this. So clicking through some of the dashboards, there might be a public communication element. So obviously there's no AI machine learning here. You've seen how we applied that. But this is information about the project. This is a way to sort of inform the public about what's happening. We can move forward to some aspects that might be useful for utility managers or might be of interest to some regulators. So are the membrane systems actually at their or under their critical monitoring limits? Are they performing well? What is my chemical removal like in a simple, digested, easy to access form? What is my energy usage like? And then I'll finish up on this. So we did put that all together as part of this USBR grant. And then the main machine learning component was that future prediction of permeability, and the potential for optimizing chemical usage was one thing we flagged as probably the most likely and most useful application of this for an ultrafiltration system, depending on where you were in the project. So I wouldn't say that in future, we could use a lot of this data to actually design better systems to remove some of the conservatism that costs money. But I don't think we're there yet. So with that, I'd like to hand it over to Andy Salverson to talk about sort of where we've been and other exciting things about where we're going.
Thank you, Amos. Next slide, please. So I was just going through my notes, and this all really started in earnest in 2018. So we're almost 5 years from an original concept. And in that original concept, which was some of this original funding, it was $75,000, I believe. And there was a lot of skepticism. And what's happened since then, I appreciate that. Skepticism always happens with stuff like this. And since that time, we've now developed more than $3 million of research funding into this topic. And so it all starts with this original grant from Metropolitan, and I want to acknowledge it really starts with the support from the Las Virgenes Municipal Water District and their dedicated commitment to push ahead, because we didn't know where this was all going to go. But as you've heard from Amos, it's going in a real positive direction. You're seeing the early work looking at using machine learning to optimize biological wastewater treatment, which is all part of this potable water reuse cycle. You're seeing, as I go left to right, evaluations and predicting ultrafiltration performance, flux and transmembrane pressure, and that is all about energy and then chemical use. And then the latest work now with the United States Bureau of Reclamation and the National Alliance for Water Innovation. These two projects are running in parallel. They're 3-year studies, and they're looking at the whole picture now. So what can we do more with the ultrafiltration? What can we do with reverse osmosis, which, as we all know, uses a huge amount of energy? And by the way, that UV advanced oxidation process at the end also uses a lot of energy and can stand to have some optimization. So we're looking at those 3 things, but it's not just efficiency. It's water quality, and it's confidence, and it's transfer of knowledge from one generation of operators to the next. And so if you go to the next slide, Amos, I want to highlight just a short little bit on both the USBR and NAWI projects. So this is just some early results from the NAWI work, where we're using a multivariate statistical process monitoring approach, MSPM. By the way, there's so many acronyms with machine learning, it can kind of set you back. But this concept here isn't just looking at one analyzer, it's looking at multiple analyzers that maybe have, you may not have a significant confidence in, but combined, they can tell you that something's happening ahead of time. So we're using this MSPM process to predict wastewater treatment plant effluent quality changes well ahead of what we would know if we just had one analyzer running. And so example here is using different parameters related to membrane filtration, whether it's permeability or turbidity, and also wastewater treatment plant effluent quality like ammonia, to know that there's a problem before it happens. And then that allows us to take corrective action before a poor water quality hits an advanced treatment process. Next slide, please, Amos. Jumping over to the United States Bureau of Reclamation work. So that prior slide, I should say, that data was from the Las Virgenes Municipal Water District. This data here is from the United States Bureau of Reclamation project, and looking at extensive amount of microbiological and water quality data downstream of a membrane bioreactor, and using 6 data sets which have a relatively poor correlation, but when you put them together, they're able to confidently tell you if you're meeting a specific pathogen treatment credit. So we have this term LRV, which is log removal value, and through analysis of this kind of data, these multiple data sets, we're able to have confidence, are we above or below a certain threshold? In this case, our threshold is 4 LRV. It could be anything, but if I go to the next slide, I'm just wrapping up and we can have any kind of questions and discussion. So this research today stemming from this initial grant shows significant promise. There's more regulatory confidence that we can see. There's operational support. There's data security is a big part of this, and we're demonstrating how to do that. Now, I take a moment and just reflect on that. It was a concern voiced by the Las Virgenes Municipal Water District. How do we maintain that data security? And so what you see in this loop is that the advanced treatment process in the left, it generates the information and it's sending it to the cloud. And that's coming from SCADA, but it never comes back to the SCADA. It lands on an iPad or another digital device where the operator then learns from that and says, look, I need to make these changes. It'll improve my efficiency, and the operator makes those changes. So that not only maintains the knowledge and the growth of the operations staff, but maintains that data security. So overall, though, it's all very exciting, and we're very appreciative for all the support we've gotten. And I think we can move on to any questions and discussion if there's out there.
Fantastic. Thank you, everybody. We did get some questions in the chat, in the Q&A. So please put your questions in there, and we'll try to get to them. We answered one before from cost savings. Why don't we go to this one? Amos, this is from James Farrow. Amos, can your team also start to estimate O&M cost savings? And you answered that partially during the presentation, but maybe you could dig into that a little bit more.
Yeah, that's going to be difficult. One of the things we have realized is that there's probably always going to need to be a site-specific data fitting and validation of these models, because there's no such thing as a typical wastewater. What we've done at the Los Virgenes demo is we showed a potential 60% savings in membrane cleaning chemicals. So that percentage sounds good. Hypo is not the most expensive chemical in the world. And unfortunately, membrane cleaning chemicals, they're not your biggest use. If you want to look at optimizing chemical usage in terms of cost, you've got to look at these mainline dosing chemicals. So maybe the hypochlorite you add to make chloramine, because you're going to use a lot more hypochlorite for that than you will for sort of periodic cleans of membranes on a full-scale system. Now, that is something we've sort of looked at as part of this. So we did vary chloramine dosage quite significantly down to 0.5 milligrams per litre as a target instead of 2.5. So that's an 80% reduction. And we were surprised at how good the results were. And so I think we might see a bit more from that in future studies. So that's where you get the biggest bang for your buck, is on those process dosing chemicals, not necessarily on the cleaning chemicals. And this sort of tool might give you confidence to make those decisions. We thought everything was going to fall over when we dropped the chloramine that much, but the reverse osmosis didn't foul. The membranes didn't foul that badly compared to the status quo, and the UV transmittance downstream actually went way up. And so you're talking about multiple potential savings. So savings on UV energy, no impact on RO, reduced chemical consumption. So we're not ready to put a number on it yet. I will say that number is going to be site specific and we'll need some training, but there is pretty significant potential there.
Great. Thank you, Amos. We got two questions from Peter. Actually, one shout out to Los Virgenes, and I agree with that. It takes tremendous resources and finances and funding to do this. Starts at the top with David Peterson and John Zhao and Daryl. So congratulations on running a fantastic study here. So I totally agree with you, Peter. But then Peter does have a question that I'll just read it. NAUI is considering more investment in working with the water industry to create cleaner and more standard data ontologies for water treatment plants, basically standardized definitions and naming conventions. What issues did you encounter with consistent data standards? And would you consider this a problem area?
Yes, big problem area. Different SCADA reporting frequencies, different data logging frequencies, not having a standard at the moment about how much data is enough to train these models. We've sort of flagged that as a research question. The data from Los Virgenes, we just took as frequent as we could get. Now, the recommended changes for the data-driven model optimization, we didn't want to put an unnecessary burden on the operators, but we sent them a new recommendation every 30 minutes. So do we really need data every 2 seconds to make a 30-minute recommendation? The answer is probably not. But I think there's still a lot of work there on how frequently should you sample to make a meaningful recommendation. And the less you can sample, the better it is for cloud data storage, the quicker your processing speeds are going to be. So that's a huge issue before you even get to standardizing calculations. Like, there's a lot of people who like to normalize reverse osmosis performance differently. So we've got our way. We use the ASTM model. Some people do other fancier things. Some different vendors do different things. So there's still a huge scope for a discussion of that.
And I'll just add, this may look polished, but there's a lot going on underneath the water here, and there's still a lot of development in every aspect that we've shown. So there's definitely savings, whether it's 10 or 15 or 20% in the wastewater plant, You see some savings on chemical addition. But there's so much of the components of this that is not standardized. So I think the first step here is just proving like we are that there's benefit. And then from there, we do have to work on some kind of standardization method.
Great. We have a question that Mr. Erdal asked, but it looks like Andrew is typing a question. Andrew, why don't you answer that live?
Yeah, sure. So yeah, so what models are we using? And I'll just rattle off a few. So Amos is the process guy. I'm the project manager, but our modeling people are not on this call. So we've got we're working with different models depending on these different projects. So the DDMO model is a model developed by Yokogawa. We have model predictive control. We have supervised machine learning, principal component analysis. It's actually a modified PCA, and non-parametric statistics. So that's my list, and I'd be glad to talk to Ufuk more about that and share the details when I can get them from our modeling guru who's not on this call.
So
Great,
there's
thank
existing Python and R libraries for machine learning, and the default approach seems to be to call on those pretty powerful tools and to use every single machine learning model that's in that library and see what sticks best. I've not seen a more systematic framework than that, but it seems to work. One of our internal data sort of management teams, the Blue Planet group, have sort of realized that random forest as a machine learning model keeps coming to the top. We can't tell you why. We'd love to be able to tell you why, because that could be really helpful. I mean, maybe it is possible to start shortlisting based on a mechanistic reason why certain machine learning approaches are better for certain processes, but I think that will require a pretty big lift to actually start answering and making recommendations about that.
Great, thank you, Amos. This next question, I think it's from Metropolitan, is from McKenna Henderson. McKenna, we don't have the right people at Metropolitan to answer that question right now. We've seen dozens of AI technologies for asset management and condition assessment, but I'm not the right person, or I don't think we have the right people here to talk about that. But so we'll reach out to you separately and see if we can get an answer to that. We have a next question is from Megan Plumley. Hi, Megan. So I'll read it. As utilities try to implement the more basic smart machine learning and AI controls, the later more complex, what is the role to be played by software vendors who hold the AI versus engineering consultant?
Maybe I'll give that a crack first, but I think that'd be good to hear the Las Virgenes perspective on this. So our understanding is that technology providers such as Yokogawa as one, they're looking at this as a software as a service program. As consulting engineers, I'll just give again the Carollo perspective, and there's probably others. We're looking to design the treatment systems, so I'll use the term, so they're AI ready. So we're not necessarily looking to develop the software ourselves. We want to make sure that the engineering systems are ready to take the software and use them. But let me turn it over to John and Daryl, see if you guys have things on that.
Yeah, from an agency point of view, the owner of the facility, the contemplation process is the same as, procure specialized equipment. Once you make a decision who you're gonna, which equipment you can procure, it's pretty much sole source from maintenance to upgrade. So we, as a utility, we like to have a very good track record, and then we rely on advice from engineer like Carollo to kind of turning all stones in the industry, see what their recommendation will be, and then based on those we'll make that decision. But either way, you can't defer that decision because that's the efficiency and reliability. And I think we have the tools, if you're looking back, how the decisions made for specialized equipment we all use, for SCADA, whether you use Modicon or you use Allen Bradley. You have to make that decision and you just stick with it.
I'll also add from the operations end, I think working with this study has been very important for the operations staff to have their input on what software works best for them. And working with Amos and Andy through this whole process at both the demonstration facility and the wastewater facility has given both departments the opportunity to work together and really get in to know the programs and how the AI is going to affect them, and they could make and have a very, very strong input on the selection process.
Great. Thank you both. Amos, you got a job offer from Peter, so congratulations. Next question is from Anthony Pimentel. Do you see any regulatory barriers to employing further machine learning or AI optimization model for full-scale water treatment?
I'll give a shot at that. The reason we try to get ahead of a regulatory is because we want to generate the data and to influence the regulatory rulemaking process. There's old saying says, if you're not at the table, you may be in the meal. So we're taking the first step with support from Metropolitan to generate the data, and therefore we can influence the rulemaking. And currently, at least in California water reuse, a lot of log removal regulations is based on what if scenario. What if that doesn't work? What if that doesn't work? Therefore, you have to comply with 12-10-10, 12 log removal and for this and that. So we're hoping with a solid research in AI and machine learning, sometimes you may be able to reduce cost if you provide a confidence to the regulators. Any other addition, Andy or Amos?
It's the cybersecurity, and when do you actually let the thing control itself? So when do we get off the SAO onto the fully automated, so semi-automated, fully automated, and what criteria should you use around that? I think we're still a bit ignorant to it. And then also these challenges of trying to use machine learning in a way where you can check its work, where you can check its calculations. That I think scientifically, we're by no means advocates of it. We've tried to sort of break it through these studies, obviously made it difficult, tried to see where the faults and errors occur because we're not confident with it yet. And we want to use these opportunities to try and define the limits of where we'd be comfortable even using it in a semi-autonomous circumstance.
Okay, thank you for those answers. I think we have time for one question with a lightning answer, and then we'll wrap up the webinar. So next question is from Steve Waite. Question is, hi Steve, what parameters upstream of the plant and other parameters inside the plant would you like to have access to, and what decision-making process could be improved?
So you asked for lightning, and I don't know if I can do that. And
Okay.
but I'll give you a shot. So one of the things that we saw early on is there's not enough analyzers, one, and there's not enough analyzers that you trust, two. So if you look at the original activated sludge work at Las Virgenes Tapia facility, we would have loved to have understood the water quality going through each of their parallel basins that are in operation, because things can change between them. So one of the Achilles heels of this machine learning artificial intelligence is not having enough analyzers and not having analyzers you have confidence in. Amos, maybe something from you on that?
We're still trying to figure out the short list. We've got a few ideas, but at the moment we work with what we can get access to and see if it sticks.
Okay, well, I'll tell you what, I'll make an executive call here. Maybe we'll go 1 or 2 minutes over because we do have some other questions that I think we are important to get to. So, and we still have people hanging on here, surprisingly. So next one is also from James Farrow. Hi, James. What are your thoughts with how to accelerate the learning process for some processes that are a better fit? You had several a several month long training process, and he wanted to know if that was correct.
So how quickly could you get confidence and fit a model? That's another good question to lump in under Peter's question of, we need standards. Like, how long is good enough? If you ask the scientists, they'll say, oh, I need 2 years of data to predict the next month. And that obviously doesn't seem like it's weighted the right way. So there's no good thing. I think an integrated model, which was informed by multiple sites with a very, very, very similar design, may help, because it'll give you a wider range of operation. But that's really difficult to get as well, because there's no such thing as a standard wastewater and no such thing as a standard wastewater treatment plant design. So that's going to be hard. I think the shortest period that we've been able to demonstrate was that sort of 3 months of data from the Las Virgenes demo used to predict all of December. So July to November, and then they tell me what December is. And that seemed to work okay, but the feed water there was very stable. So could be a limitation.
And
Thank you.
if I could just add, I think there's an opportunity once the longer training set is established to redo the model on maybe a weekly basis. There's an opportunity to do something like that.
Okay, I think that's all the time we have for today. We do have some questions that we weren't able to answer, and I apologize to those. We'll, if we can identify you by the name, we'll try to get answers for you. We'll work with Andy and Amos. But I want to just congratulate all the presenters, John, Daryl, Andy, Amos. Fantastic presentation, fantastic study, like people have posted in the Q&A. So I want to thank you all for the time of putting this together and for the work that you've done. I also want to recognize the Metropolitan FSA staff. That includes Christina Vejo, Patrick Murphy, Jonathan Jordan, Matt Hacker, Stephanie Franco has been helping out. Also Nicole Delgado, Teresa Gonzalez, Ryan, Roman, Lauren, and Terrence. And without their outstanding work, the FSA program in this webinar would not have been possible. Finally, I want to thank all of you for taking time out of your day to participate in today's webinar. We had great participation, and I think the next webinar that is related to the FSA is going to be with the Water Research Foundation on, I believe it's April 20th. They'll be sending out more information, and you can probably find it on their website. Thanks once again. Thank you, everybody, and see you next time.
Thank you, Warren.